extreme values of functions in applications of mathematics involving functions, and in general in physics, right? So in physics, you have a lot of functions. The most simple function you can imagine is your XA101, where you are dealing with the kinematic equation. So the kinematic equations are example of functions, right? Functions of velocity as a function of time, velocity as a function of positions, and position as a function of time, acceleration as a function of time, etc. So these are functions that carry a lot of information. For example, you have a functions of position as a function of time, right? So you have a position as a function of time, and at different locations and at different time, then from the graph of the position, you can tell where is the current location of the object. And then from that graph also, you can work out how long the person has traveled. Where is the location which is furthest away from its initial point? What is the location where it is closest to the initial point at some time later? So in many occasions, you need to find out what is the largest number in the functions and what is the smallest number in the function. So it's happened very often, and we need to know these numbers, right? So given a function in its domain, you want to know what is the largest value of the function within the domain, the smallest values within the domains. And other than that, there will be also local maximum and local minimum. So local maximum are the largest number around its vicinity, right? So we are going to talk about these largest numbers or smallest number. So we have a term for that in the functions. The largest number for a function within its domain is called the global maximum. Sometimes we call it another name, right? So the extreme values of a functions refers to either the largest or the smallest, and the largest number or smallest number sometimes refer as extremums. Extremums refers to largest number or smallest number. Furthermore, you could have local extremums and global extremum. Okay, so we're going to talk about these distinctions in today's lecture. So it shouldn't be very difficult. Okay. Back. Now let me go to the next slides. So we have to first define what you mean by extremums. Okay, so I have consumed recording. So we consider functions within. Oh, you can't hear me. Okay. So can you hear me now? Is it better? Still cannot hear?
Yes, doctor can hear.
Yes, doctor
Okay.
can hear now.
So I touch. Good, thank you. I just touch my USB, just a small touch, and suddenly it just gone become disconnected. So anyway, we are talking about the definitions. So in physics or in mathematics, you always have to define properly before you can already can hear from me. Yes, you can. Okay. So the definitions has to be properly defined before we use it. So this is what mathematics do, right? You always define what you mean by a maximum and minimum. And as I mentioned, there are two types of extremums. That is absolute extremum. So absolute maximum and absolute minimums are the two types of absolute extremums. Extremums refer to either maximum or minimum. So sometimes the absolute maximum or absolute minimum is also known, or sometimes it's called global. So when I say global maximum, global minimum, it is also refers to absolute maximum and absolute minimum. So imagine you have some point, see if I can draw on it. So if you have some functions and you define the domain of the function, so let's say this is a domain of the function dx of the functions, then within this domain, the values of the function which is largest at some point, say a point C somewhere here. Let's say you have a values C and the values of function here is fc, then if the values of f at c is always larger than all the other values within the domains, then this point of c is called the absolute maximum. It's quite easy to understand, right? So if you have a point fc where the values of the function at c is always smaller than any other functions, any values in the function within the domain, then the point c is known as the absolute minimum. So this is a very simple example, right? So you look at the cost function, the absolute maximum is this point, and the absolute minimum for the cost is this point and this point, because at the absolute maximum, for example, at this point, all any other values of the function is smaller than the values of the function at this point. So for a sine, this is the absolute maximum, this is absolute minimum, and this is a special case where the maximum and the minimum is well defined for a function within an closed interval. So there are also some other complicated situations like this one, where you may not have absolute maximum or absolute minimum within the domains of the function. So to be sure, if you have a closed interval function where the function is also continuous, like in the case of sine and cos, we're talking about a closed interval, then you would have absolute maximum and absolute minimum. But for other cases like this, for example, A, you look at A, this is an intervals which is not closed. So it is a domain which is like, let me see, I did, okay, which is like you start off and you end up with negative infinity to positive infinity. So this is example of an open interval. So within these open intervals, you don't have any absolute maximum, but you have only absolute minimum, okay? So you look at part B, so where the function is defined, right? So it's defined for an closed interval. This is a closed interval, which is within 0 to 2. So the x is defined for a domain which is closed from 0 to 2 inclusive of them. Therefore, in this particular case, this is very similar to this example where you have a closed interval and the function is continuous. Then you have absolute maximum and you have absolute minimum. So this is kind of easy to understand. But there will be situation like case C. So where case C, you have an closed interval, sorry, not closed interval, a closed and on the right, which is 2. So here the domains inclusive of 2, and the left hand side, it has the side which is an open open 0, which means that 0 is not included in the domain. So the domain of this function is defined as from 0 to 2, 0 is not included, 2 is included. So in this case, the function is x squared, then it has an absolute maximum, but it doesn't have a absolute minimum, right? So you cannot say 0 is the absolute minimum. Why is that you cannot say 0 is an absolute minimum for this function? The reason is because 2 is not included in the domain. So the function is not defined at 2. So what is the smallest possible value of this function within this interval? It's not 0, right? Because x equals to 0 is not included. So if it's not 0, then what it is? You think of some number which is defined within the intervals of open 0 and with 2 included. So any number which is close to 0 would not be the absolute minimum, because there will be a number which is smaller than any number that you choose for x, as long as x is not 0. Right? Say, for example, you say, okay, x is equal to 0.000001 is the lowest value for the function. Then you can think of another value which is smaller than the value that you mentioned. So mention any value of x. You can always have a number which is smaller than x to give you the minimum of the function at y equals to x squared. So in this particular case, it is sort of like abstract because the function is not defined at x equals to 0. Therefore, you can't have an absolute minimum for this function. So this is another extreme case where the open intervals is defined for the function from 0 to 2. So you can't have an absolute maximum and you can't have an absolute minimum. Okay, so again, before I leave these slides, I just want to let you know the absolute extremum for a functions is defined based on the entirety of its domain. So when you define an absolute minimum or absolute maximum, you are referring to the whole domain and find what is the smallest value and the largest value. And for a special case where the function is continuous and defined within an closed interval, then you could have an absolute maximum and absolute minimum. Otherwise, you may or you may not have a absolute extremums for that function. Okay, so then we have to go to another very straightforward thing, right? This is what I mentioned earlier on. If you have a function which is defined interval, say a closed interval, let me draw it properly. So if you have a function which is defined on a closed interval of a and b, so a and b could be a the domain or could be not a domain, as long as it's an interval and the function is defined within this closed interval. Then in addition to that, the function f that is defined on this interval is continuous. Right? It is continuous and it is defined on a closed interval of a and b. Now, as long as these two conditions are fulfilled, then we are very sure that for this function within the intervals of a and b, there must be an absolute maximum and there must be an absolute minimum. Okay, so when you mention the axis, so this is a theorem that guarantees the existence of the extremums, right? So it doesn't tell you where the extremum is, but it guarantees you that you must have at least one absolute maximum and one absolute minimum somewhere between A and B, right? Inclusive the point of A and B as well. So it must be somewhere, let me draw it. There must be somewhere within this closed interval, a point x1 where the values of f at x1 is the minimum of, is extreme minimum. And there must be another, at least one point, say x2, that the values of f at x2 is the absolute maximum. So it must exist some number. And let's say you call capital M as an absolute maximum, then it says that f at x2 is the absolute maximum. So anyway, you could have this example, like you have a closed interval defined for the functions in a and b. You look at this this diagram. So it's a typical situation where the function is well defined within interval a and b and is continuous. And for sure, there must be at least one point where the absolute maximum happen, one point where the absolute minimum happen. And in this particular example, the absolute extremums happen in interior point. Interior point means the values of x that is not at the extreme is called internal point. So this is an example where the extremum happen in the internal point. You could also have a situation like this where the extremums is happening at the extremum is happening at the endpoint, right? So there is no internal point where it's maximum or minimum. So this is another example where the local maximum, is happening, well, the absolute maximum is happening within an anterior point, whereas the local minimum is happening at the endpoint. And in this particular case, the absolute maximum is happening at the extremums, at the endpoint, and the local minimum is happening within an internal point. So this is an example that I try to illustrate to you. If you have a closed interval for a continuous function, the absolute maximum could either happen at the internal point, or it could happen at the endpoint. So either way, we just don't know. But for sure, there must be an absolute maximum and there must be at least one absolute minimum. So you can imagine another situations. I don't have any space to draw. Okay, maybe I draw on another place. So let's say you have a situation like this. You could have, say, a function which is defined between a and b that looks like this. Right, it looks like this. So in this particular case, you have okay, so I think I mentioned something which is not right just now. So there is only one absolute maximum in this case, and there's one absolute minimum in this case. Now, could you have a situations where you have a function which is continuous within a and b, where you have more than one absolute maximum? The answer is yes. So if you look at, let's say, let's see if I can find any examples here. No, maybe I just have to invent myself. So let's say I have a function that is, say, something like this, say, something like this. Okay, so this is, just want to find out an example where you have two local extremum. So this is an example where you have two absolute extremums, right? So here you have a absolute minimum for the function cos x at this point and this point. So it is possible that you have a closed interval of functions and you could have more than one absolute minimum. You could also have more than one absolute maximum as well. But all the example that is mentioned here, you have only, say for example, these slides. It is showing you only the special case where there's only one absolute maximum and one absolute minimum. But in principle, you could have more than one. Okay, you have more than one absolute maximum or more than one absolute minimum. So in that case, can you apply this theorem and see if you can apply this to a continuous function defined within a and b that is taking the form of a constant function. So you can imagine you have a constant function, right? You have a constant function, say y equals to 2, right? So, and it's defined, say, for some closed interval of a and b, say 1 and 2. So tell me, how do you apply these theorems to a constant functions? So the theorem says you must have at least one. Now it didn't say that, but at least it didn't say you have to have a one, but it says you must have an extremum value m and extremum values of small m. Okay, so in this particular special case, every single value within a1 and 2 for the function y equals to half had attained an absolute minimum. Is it absolute minimum? Let me look at the definition first. Okay. Oh, okay. I think I made some stupid mistakes on my slides. Okay. Excuse me a minute. I have to go back to my iPad. Okay. Now, absolute maximum and absolute minimum is defined to be a function which is equals or larger than any other values of the functions, right? So you have this equal sign, equal or larger sign in the definitions of the absolute minimum. So if you were to apply this to a case of a constant function, right? So if you apply it to a constant function using theorem 1, every single value within a constant function is an extremum. Right? It could be both minimum or it could be both maximum at the same time. Right? So the extreme value theorem is applied to a constant, then every values on the functions is an absolute minimum, because the absolute minimum fulfills the definitions of this condition, right? Absolute minimums is a number which is smaller or equals to any other values, because all the values are constant. So the values of the function at all point is just equal to any other point. Therefore, by definitions, all points on the constant functions is an absolute minimum. And for at the same time, all the values of the constant functions are larger or equal than the constant functions. So in that particular case, it's equal, right? So it's equal also fulfill these conditions. So what you say is that all the values of the functions in the constant functions are all absolute maximum. So you have, in that case, infinite numbers of absolute maximum, infinite numbers of absolute minimum for a constant function. But for a function which is not constant like this, the numbers of absolute maximum and the function of absolute minimum is finite. Here you have only one absolute maximum, two absolute minimum, one absolute maximum. And then you have one absolute maximum and one absolute minimum only. Okay, so that is what I want to tell you about the extreme theorem. It's just very simple. For example, you just say you have a collection of all the students in the class. Then you sort the students according to their age, the one who are born earliest up to the one who born latest. So this is not a good example, because this is not a discrete number, but that is the best I can think of. Not, yeah. So you line up all the students in the class from the youngest to the oldest. Then it is always possible that you must have someone who is youngest and someone who is oldest, right? So the collections of all the students in the class, there must exist someone who is the youngest. If that two person turn out to be a twin, which is born at the same time, same second, then you have two youngest person, right? Same time, same thing also happens to the oldest person, right? You must have at least one person who is older, right? This is the idea of the extreme theorem. So sometimes it's just like a repetition of a trivial statements. A function which is continuous, it must has an absolute minimum, at least one. It must have an absolute minimum, at least one. Okay, you have more than one, but at least one. And then at that particular maximum minimum, then the values of the f at 1 is always smaller than any other values of the functions within the domain. And at the maximum, at x equals to x2, then the values of f at x2 is always larger than any other values of the function. So that is basically what this theorem says. So if you read about this theorem more carefully, this is just what it meant. I spent a few minutes to explain what it is, but you could be able to understand this as well. Okay, so let us look at and what we call a counter example to the mean theory to this theorem. The theorem says if you have a closed interval of a functions which is defined within that closed interval, there must at least one absolute maximum, and there is at least one absolute maximum. Now, these theorems, if you read it from the reverse directions logically, it also means this. If the functions is not continuous, then the statements will not be correct. Right? So these conditions that a function must attain at least an absolute maximum and attain an absolute minimum for a function which is continuous within the interval of closed interval of a and b. But if it's not continuous within a closed interval, then it doesn't guarantee you to has an absolute maximum or absolute minimum. Do you understand what I mean? So this is mathematics, right? Mathematics is very rigorous. It say if A, then you B. If it's not A, then it's not guaranteed that you will have B. So here, A means a function that is continuous on a closed interval of A and B. If that is true, then you would have absolute maximum as absolute minimum within A and B. But if a function is not continuous within A and B, then there's no guarantee you would have an absolute maximum and absolute minimum. So you look at these situations, then you say, would that be an absolute maximum for this function? Is defined, it's a function, right? It's a function defined to be y equals to x when x is between 0 and 1, and at the point x equals to 1, the function is defined to be 1. So this is a function which is not continuous at x equals to 1. So within the intervals of 0 and 1, inclusive of 1, so within this closed interval, you couldn't have an absolute maximum. There's no guarantee you have an absolute maximum for these particular examples because the theorem 1 does not apply. Theorem 1 only applies if a function is continuous, and since this is not a continuous function within a closed interval of 0 and 1, then there's no guarantee you could have an absolute maximum. And indeed, as I mentioned earlier on, for this particular case, you don't have an absolute maximum. Yes, you do have the absolute minimum, but this is actually in general not guaranteed because the functions is not continuous within 0 and 1, although it's continuous at 0, but it's not continuous at 1. So here it doesn't has a absolute maximum. Okay, so this is just an example to illustrate to you when you apply a theorem, you must make sure you know what are the conditions that guarantees the applicability of the theorem. So the application of the theorem is that you must have both to be continuous at the point A and B, inclusive A and B. Only then you will guarantee an absolute maximum and absolute minimum. So in this case, it is not, right? So it is not continuous within an closed interval of 0 and 1. In particular, it's not continuous at 1. Sorry. Just a moment, okay? Let me resume. Okay, so this is a counterexample that there's no absolute maximum because the condition doesn't apply. But how about the local minimum? The local minimum happens to exist. It's just a coincidence, right? Because the statements that it is continuous on A and B is not true. Therefore, you can't apply the theorem 1 to obtain the absolute maximum. But this doesn't guarantee either the existence of a local absolute minimum as well. Okay, now it's a bit subtle because this is logic. When you say logic, it has to be applied and be true throughout the whole domain, right? So the domain is throughout the whole intervals. The whole interval is 0 and 1. So you can only make a statement that this is true only if it is continuous on 0 and 1. Since it is not, then you just cannot apply the theorem 0, right? So if you apply, then you may get a negative answer. If you get a positive answer, it doesn't mean that the theorem is guaranteeing the existence of that absolute minimum. It's a bit subtle, so maybe I should not continue to talk about this to just avoid confusion. Now, as I mentioned earlier on, you could have an absolute maximum, an absolute minimum. You could also have a situations where you define a local minimum and local maximum as well. Now, local maximum and local minimum are defined slightly different than the absolute maximum and absolute minimum. The absolute maximum and absolute minimum is defined by referring to the values of the extremums with respect to all values of x in the domain of the function. Right? So this is how the absolute maximum is defined. So you compare all the values of the function for x in the domain of the functions. But for local minimum and local maximum, you define the local maximum and local minimum for all the x that is lying just within the vicinity of some local point C. Right? So you compare the values of a function at the local point C, say here C. So you compare the values of x, which is just next, left hand side and right hand side of C. And if you find that if the values of the function at C is such that its value is the neighboring values is always smaller than the values of f at C, where x is just somewhere nearby, left and right of C, then we call this an local, we call FC a local maximum. And if you have a case where the values of the function around C, where the values of the function is always equals or larger than the value at C, such as these situations, like this one. So all the values around E on the left or the right, the values is always larger than the values of the function at C, then this f at C is called an local minimum. Okay, so before I proceed on, just a word of clarity, that when you mention local maximum, local minimum, absolute maximum, absolute minimum, usually we refers to the values of x at the values of x where the local maximum, local minimum, or the absolute maximum or absolute minimum happens. Right? So you just say x equals to C is the local minimum, for example. But to be more specific, a local minimum or local maximum, absolute maximum or absolute minimum has to be properly specified in terms of a pair of the values of x and the values of the function at the point of that extremum. Right? So formally, a local maximum is a pair of x and the values of f at x, where that local extremums happen. Okay, so in proper manner, when you say when you answer where is the local maximum, local minimum, extremes values, you have to specify the pairs of x and the values of the function at that x as well. Okay, so once we have understood what you meant by a local minimum and local maximum, then we proceed to the next slide. But the values of local maximum and local minimum is necessarily an interior point. Okay, so here C is an interior point, and it does not include the endpoint. Okay, so if you look at this example, the C, DE or D are the example of a local minimum, right? So these are interior point. Okay, so before I leave these slides, this is just a good example of showing you what are the local maximum and local minimum. So for continuous functions between A and B, you must have an absolute maximum and you must have the absolute minimum. So here, this is the absolute maximum and this is the absolute minimum. Absolute maximum, absolute minimum. And you could also have local maximum and local minimum. So this is a local maximum, local minimum, and this is a local minimum. Okay, so a local minimum, no smaller values of f nearby. But yeah, okay, so this is an example of identifying local maximum, local minimum, absolute maximum, and absolute maximum, absolute minimum for functions defined on X. Okay. So the next thing we want to talk about is the statements of theorem 2. It says if you have a local maximum or local minimum, then the derivative at that point must be 0. Okay, so if the point is a local minimum or local maximum, then the derivative at that point must be 0. But this does not say if the derivative is 0, then the point has to be a local extremum. No, it doesn't say that. Now this is example where you have a continuous function and you have a local maximum, right? So this is interior point, and for sure you have a local maximum. So if you go from the left, the slope is positive, and when you go to the right of C, the slope become negative, right? Sorry, yeah, I think it become negative. So if you follow the slopes, it go from positive, goes to 0, then go to become negative. So when you cross from negative to positive, when the slope cross from negative to positive, there must be an intermediate point where the slopes will take on the values of 0. So this is a very intuitive understandings. That is, if you have a local maximum in this case, then the slopes from the left approaching the local extremums to the right, then the slopes will change sign, right? So when it change sign, then the slopes must cross the 0 value. So that is what this segment is about. It says if there is a absolute, if there is a local maximum or local minimum, then the slope at that local extremums must be 0. Okay, so this illustrates the situation. So you can explain this quite easily, but this is only true if you already know that that point is a local maximum or a local minimum. But if you do not know that it is a local maximum or local minimum in the beginning, then you can't tell for sure that that the point where the slope is 0 must necessarily means it is a local extremum or local minimum. No, so you have to be very careful when you interpret theorem 2. It says if A, then B, right? So A here means if you know it is a local extremum, then B must be true. The B here refers to the statements that the derivative is 0, right? It doesn't mean if B is true, then A is true, right? It doesn't mean if the derivative is 0, then it must mean it is a it must be a local extremum. No, okay? So you have to be clear when you study mathematics, the idea, the flow of logic goes from A to B. When I say it's A, if A, then B, it doesn't mean if it's not A, then it's not B. No, this is not true, okay? So if it's local maximum, then the derivative is 0. If the derivative is 0, then what happened? No, we don't know because the statement doesn't go in the opposite direction. If A, then B. If it is not B, then what necessarily means is actually something else. Okay, so so this is another example. So let's see if I have an example. This is example where you have an derivative. So let me see if I have an example that shows, yeah, this is an example. So you look at this example, obviously at this point you have a derivative which is 0. Here you have a derivative which is extreme, right, which is infinity, which is not defined. So this is a good example to show if you have a derivative which is 0, it doesn't mean it is an absolute, it is an local extremum. Okay, so remember this. If it is derivative is 0, it doesn't always means it is a local extremum. But in some cases it is, but it doesn't mean all cases are like that. Okay. Okay. So we then have to define another thing called critical point. Now, critical point is an definitions again. Now we need all these definitions in order to proceed to the next agenda. Now, what is the next agenda? Before I mention what is critical point, the agenda is this: is that we always want to know where is and how to find out the local maximum, local minimum, absolute maximum, and absolute minimum. We need to know functions where the extremum happen. So we learn different definitions and we learn different theorems so that later on we can use this definition and use these theorems to help us to locate the extremums, whether it's absolute or minimum, whether it's absolute maximum or absolute minimum, local extremums. So here we actually want to learn up this definition for critical point so that we can use this definition to help us to locate the absolute maximum or absolute minimum of a function within a domain. So this is what the definition of critical point is for. Critical point is defined as a function where the derivative is 0 or undefined. So either way, if a function has zero derivative, or if a function has a derivative which is not defined at a point, then we call that a critical point. So
the applications of the procedure to calculate the absolute values of the extremums, we illustrate it with an example too. Right? So you have a functions that looks like this, fx equals to x squared, and is defined on intervals of -2 and 1. And let's just see how you would calculate the absolute minimum and absolute maximum for this function. Okay, so the function that we are dealing with is fx equals to x squared, and x is to be defined on the intervals of -2, 1. So usually when you do these questions, it helps if you can display the graph of the function. And since this is a very simple function, let us display it. So the function will look like this. So it's -2. Then the function of x squared, when you start from -2 to 1, then the function will look something like this, and it goes to 1. Okay, maybe I should draw this more carefully. Okay, so this should be just a straight line like this, and the function goes from here, and then it should touch 0, and goes to 1. Okay, so here it's 1 plus 1, and this is a value of 1. Here it is a value of 4. Okay, so this is a function that we are expected to get. So before you can calculate the absolute values, you should see from the graph that you expect the answer to have absolute values, which equals to, okay, so the values for the absolute maximum is easily seen to be the number. So it should be 4, and absolute minimum for x within -2 to +1. So this is +1. Okay, so the minimum should be then just equals to this number. So this should be the absolute minimum. It should be 0 and 0, and absolute maximum should be -2 to 4. So before you do the calculations, this is what you expect in the beginning. Before you do the calculation, you sort of expect an answer. So let's try to calculate the maximum. It should be quite straightforward. So you would want to calculate the derivative of the functions. So if the function is x squared, the derivative of the function is x2. So once you have calculated the expressions for the derivative, next thing you want to do is to calculate the critical point. I write CP to represent critical point. So the critical point is a values of x such that f prime is either 0 or undefined, right? So it's obvious that if f prime is 2x, then the value where f prime is equals to 0 will be just equals to 0. Right? So this will be 0. So therefore, we know that when x equals to x 0, when x equals to 0, then f prime is not defined. So this is the critical point. The critical point is when x equals to 0. When f equals to 0, the values of x at 0 is also 0 because fx is equals to -2. So therefore, we have the collections of the point at 0, 0. This refers to the values of the critical point. Then once you have done that, then you go to the next part, which is to calculate the values of x at the left-hand value. Right? So the x is defined to be intervals of -2 and 2, which is -2 and 1, sorry, -2 and 1. So we just need to calculate the values of f at -2 and see what its value. So this would be 4. So from here we have the point which is at x equals to 2 and -2, the values is 4. Then you calculate the values of the function at the other endpoints. The other endpoints is defined at x equals to 1. So this is equal to 1. So therefore, you have another point, which is at the endpoint x equals to 1 and values of f(x) equals to 1. So you have a collection of 3 numbers, which is the values of the function at critical point, the values of the function at x equals to the left-hand value, and the values of function f when x is equals to the right-handed value. So what you do is you just collect the 3 values, the values of f at critical point, the values of f when x is at the left-hand side value, and the values of x when x equals to the right-hand side value. So this is equal to 1. Okay, so once you base on these collections of 3 numbers, then what is the absolute maximum? The absolute maximum is a value when fx is the largest. So this is your absolute maximum, right? And the absolute minimum is just the smallest from these 3 numbers. So this is the absolute minimum. Okay, so from here, then you can easily write down absolute minimum. Absolute minimum is then a point which is just equals to values of 0, 0, and absolute maximum is the values of 4 when x is equals to -2. So this would be your absolute maximum and absolute minimum. So this absolute maximum, which is this one, and your absolute minimum is just 0. So this is just the result that would you go through this procedure of taking the values of the function at the left-handed point, right-handed point, and the values of f at the critical point. Right. So you pair the values of the functions at these 3 points, then the highest of the collections would be the absolute maximum, the smallest would be the absolute minimum. So it is actually quite a straightforward calculation. Okay, so for these discussions, we will look at another example, which is as shown on the screen. So in this case, you have a function g equals to 8t minus t power 4, defined on intervals of -2, 1. And you are asked to calculate the absolute maximum and absolute minimum using the procedure we just have described earlier on. Okay, so to do that, so the questions that we are going to talk about is function of gt equals to 8t minus t power 4. Okay, so it would be, okay, so in order to calculate the absolute maximum minimum, again, we just first calculate the values of the derivative. So this would be like 8 minus 4t cubed, right? So a derivative given to be 8 minus 4t cubed, it would be defined for all values of t. So there will be no critical point where the g prime t is undefined, but you have only critical point where g prime t is 0. So it is quite easy to calculate the values of t where g prime is 0. Therefore, from here, the critical point happens at a point when t is equals to, you can set this quite easily, it could be just equals to 2, let me see, when t prime, g prime goes to 0, then it will be t cubed, it will be then just equals to 2, okay? Or in other words, the t is equals to 2 raised to the power of 1/3, okay? So this will be the values of the critical point. I'll call this t equals to t0. Okay, so at t0, then the values of g prime will become 0. So at the point here, then you can try to calculate the values of the values of g when t equals to 0. Okay, so the values of this turns out to be quite a complicated number. So in order to calculate that, then I would like to use by Mathematica. So Mathematica give me these functions. I can plot the values of g, the function of g. So this is a function of g. So when you plot it, then you got these functions. And then the values of t naught is just values of 2 raised to the power of 1/3. So this is the values of the t naught. So now what is the values of g at t naught? You can easily calculate these functions by using the Mathematica. So let me try to see what is the values of t naught. Okay, so the values of t naught is actually 2 raised to the power of 1/3. So so when you press the button, the values of t naught turns out to be 1.29 1.26, right? 1.26. But remember, the functions of gt, as mentioned in the text, is only defined for t from -2 to 1. So obviously, when t equals to 1.26, 1.26 is larger than 1. So 1.26 is lying on the right-hand side somewhere here. Therefore, this is not a critical point for the fact that the critical point, the values of t naught, is lying outside the range of t where the function gt is defined. So I would say in this case, there is no critical point for these functions within the intervals of t from -2 to 1. Okay, so that is for the first thing. So once you have no values of critical point within the intervals of from -2 to 1, then what is left is the values of g at 2. So the values of g at -2, where -2 is the left-handed value for the intervals. So the values of g -2 is 32. Then you can also obtain the values of g at the right-hand value, which is 1, which is 7. Therefore, you have two numbers. Right? You have a collections of two numbers, which is -22, which is the values of the function when x equals to the left-handed value of -2. Then you also have the values of 7, where 7 is the value of the function when x is equals to 1. Right? So here is the values of x, y, g is the values of 7, and this is the number where x is -2 and g is -32. So this is the collections of the values for the function evaluated at the left-handed endpoint and the right-hand endpoint, and there's no critical point that enters here. So you don't need to list the values of the function at the critical point. Okay, so then from here is obvious that the absolute maximum is then just a number of -2 and 32. So this is a critical point. So critical point, as I mentioned, has to come in a pair that describes the locations of the x value and the y value, and the absolute minimum will then be a values which is equals to 7 happen when x is equals to 1, right? So this is the critical point for the functions, and if you refer to the graph, this is what you see, right? So this is the absolute minimum and this is the absolute maximum. The critical point, the other critical point happening somewhere here, which is not entering the pictures because the g prime would not be equal to 0 within the intervals of -2 and 4. Therefore, this illustrates the applications of the functions of the procedure to obtain the critical points for these functions. This is example 3. Okay, so we go to example 4. So example 4 has another function that looks like this. Fx is equals to x power 2 over 3 defined on the intervals of -2 to 3, including -2 and 3 as well. So let's just see how we can find the absolute maximum and the absolute minimum for this function within these intervals. Okay, just hold on for a moment. Okay, so let us begin our evaluations for the x prime for these functions. So x prime would then be equal to 2/3 x power minus 1/3. So this is the expressions for the derivative of the function. So let us now proceed to calculate the critical point for this function within -2 and 3. So what is the critical point? So it is to be understood that the functions of x to the power of -1/3 has no critical point where f prime equals to 0, right? Because you could not have x set to exactly 0, because when x set to 0, then f prime would be, well, let me say it again. The critical point here is a point where f prime is going to be undefined, right? There's no critical point where f prime is 0. It is not possible to find a critical point where f prime is 0, but it's only possible to find the critical point when f prime is not defined, right? So if you set x equals to 0, then what do you get for f prime? F prime is undefined, right? It is undefined because you have this is equals to 2/3, and then you have x raised to the power of 1/3, right? So when x equals to 0, then the whole thing will just blow up. F prime will just blow up when x is set to be exactly equals to 0. So this is the definitions for a critical point. It is a point where the derivative is undefined. So once we have found the critical point, which is at x equals to 0, then we will proceed to calculate the values of the function at the critical point, which is x equals to 0. So this is equal to 0. Therefore, we have a critical point at 0, and the values of the critical point at the functions at the critical point is also 0. So it needs to be understood here that critical point, the derivative is undefined in this particular case, but this does not mean the values of the function is not defined at the critical point. So let me say it again, f prime is undefined. That doesn't mean f at the critical point is not defined. It is still defined because f is defined based on this one. F prime is based on this one. So if f prime is not defined, it would not automatically mean f is not defined. Here, f is well defined, it is equal to 0. So we have obtained the values of the function at the critical point. Then we proceed to the next part to calculate the values of the functions f at the left-handed value. When the value of f left-handed is -2, so you get a number. So this is just equals to -2 raised to the power of 2/3. Okay, so that's a little bit of confusion sometimes of how you do that. So this is equals to -2 raised to the power of surd3. So this is a surd3, and the values of surd3 is defined for a negative number. Okay, the values of surd3 or surd5 or any surd, which is odd is defined. So this is just equals to the surd of 3 for -2 and raise it to the power of 2. So that is the values, which is not integer, which is not complex, it is well defined. So what is the number? So the number could be easily obtained by referring to, again, my Mathematica. So let me share the screen for my Mathematica. So this is the Mathematica screen. Okay, so I have a function which is surd3, right? So this is surd3 refers to x raised to the power of 1/3. Then x to the power of 2/3 is just surd3 of x raised to the power of 2. Okay, so then this is XL, which is the values of X on the left-handed side, and XR is the values of 3, which is the values of X at the extreme. Okay, just give me a minute. Okay, so then you press the Mathematica, then you get 1.58 and you get 2.08. So this is the values of the functions when x equals to -2, and this is the values of the function when x equals to 3. So we have a collection of 3 numbers, right? So here we have a set of 0 and a set number which is, so let me show it like this, 1.5874, the values of the function evaluated at x equals to -2, and 2.08008, which is the values of the function when x is equals to xr. So you have 3 numbers, right? So the first number is the values of the critical point, then the function of f at xl, f at xr. So now it's time for us to easily identify what is the maximum and the minimum of the function. So let us come back to here. So the largest value is among these 3 numbers is 2.2008. So this is a value which is the absolute maximum. So the absolute maximum is then just a number which is 2.08008. This is the values of the functions, and the values of the x correspond to the absolute maximum is happening when x equals to 3.0. So this is your absolute maximum. And what is your absolute minimum? The absolute minimum is the values which is the smallest, right? Which is equals to when x equals to 0. So the absolute minimum, I will write it as a value which is equals to 0. So these are the values of the function at the absolute minimum, and the corresponding value for the for the values of the absolute minimum is when x equals to 0. So this is our absolute maximum point, and this is our absolute minimum point, right? So you can easily plot the functions. I think you can plot these functions. Let's see how I do it. So I'm going to plot the functions of f of x for x from xl, which is -2, to xr. Okay, so you plot it, then you got this kind of function. So this point, what is this? Yeah, this point is the absolute maximum, which is referring to this value when x equals to 3, and absolute minimum is when x equals to 0. So you have this very nice function defined from -2 to power to x equals to 3, and the largest number, which is absolute minimum, is happening here, which is equals to 2.08008 at x equals to 3, and the minimum is just, absolute minimum is just 0, happening when x equals to 0. So that illustrates the applications of the procedure on example number 4. Okay, that finish up our example number 4. That's all for this recording.